Hey guys, all right, this recording is for our unit 9.4. It's called vectors. We will leave these paragraphs alone for a little bit. We will go over that in class. So I would like for you to find your first vocab, okay? It says vector. So go ahead and scoot it all the way down. We have quite a bit of vocabulary and theorems for this unit, so I'm just going to try to get through it. And if you need to pause it to write it down, please do so. So the first one is called vector. Vector is a quantity that has both the magnitude and direction. So let me find my pen. Vector is a quantity. Oops. Tap to set up your pen. Not yet. Okay. That has both the magnitude and direction. Okay. Vector V. So most of the time we use vector V, okay, is denoted as in your book. So let me say book. In your book, it's denoted as a bold V. Okay, so if you see this bold letter V or W or any bold letter, it's used for vector. Now, because we can't, it takes too long to write bold, like, shade it in when you're writing with a pencil. By hand, we write vector V like this with an arrow. Okay, so vector V. Now writing both parts of the arrow is too long. So myself, I write just with one arrow. So if you see letters with not one arrow, an arrow with just like the top, direction, because it's just too long for me to lift up my pencil and then go down to make another one. Then if you see letters with arrows, that means they're vector when you're writing by hand, okay? Magnitude is the size or length of the arrow, okay? And remember, the arrow is used to replicate, or not replicate, is to show the vector. So it's the size or length of the arrow. The symbol of magnitude, we studied this last time, is the absolute value of V, okay? Absolute value of V. And then because V in your book is like this bold, okay? So in your book is absolute value of this bold word. In your book, they use this double bars, okay? So it's looking for the magnitude. Now when I'm writing it, I write it like this, okay? Or just to kind of keep it similar to the book, I kind of do that, okay? So some properties of V, okay? So some properties of the magnitude are, if V is a vector and if alpha is scalar, then the magnitude of vector V has to be greater than 0. The magnitude of a negative vector V is exactly the same as the magnitude of a positive vector V. Magnitude of vector V is equal to 0 if and only if, okay, so IFF means if and only if, if vector V itself is 0. The absolute value, or the absolute of a scalar times vector V, is exactly the same as if we were to take the absolute value of a scalar times the magnitude of a vector V. Okay. Then the last one is on this page is zero vector, which is denoted as bold in your book, 0. When we're writing it in class, we write it like that, okay? So zero vector, okay, is a vector with 0 magnitude and it has no directions. So it is a vector with 0 magnitude and has no directions. Okay, then let's move on to the next page. Well, at least mine is on the next page. All right, so this is just to remind us, okay, bold-faced letters. Oops, I meant to highlight that. Bold-faced letters are used to denote vectors, okay? So to kind of separate them, distinguish them from numbers. Equal vectors, okay? So equal vectors, if and only if vectors have the same magnitude and the same direction. Okay, so let's just give you an idea of what equal vectors are. Let's make a dot right here. Okay, and count up 2, 4, and then go right 2, 4, 6. So this is how you draw a vector. So you connect one dot to the other, make your arrow. Let's call it vector V. Okay. Now I'm going to draw another vector. Let's do some over here. Okay. Now I'm going to go, okay, so go up 2 and then right maybe 2, 4, 6, 7. So let's call vector W. And then I'm going to draw another vector. Let's start here. 2, 4, 2, 4, 2, go up 4. Go right 2, 4, 6. Okay. Let's call this vector Z. Okay. So these are 3 different vectors and they're very similar. Okay. The thing is that only 2 of these are the same. Okay. The 2 that are the same are vector V is exactly the same as vector Z because it has the same sides and the same direction. Okay, vector W, it looks very similar, but we went up 2 and we went over 7. Okay, so that is slightly different in direction. All right, next 5. Unit vector is a vector. What is this doing? With oh my gosh, what is it trying to do? Jeez. Okay, with, are you serious? Sorry, my computer just updated a bunch of stuff last night, so it's like behaving strangely. See? Look at that. What on the world? Unit vector is a vector with magnitude of 1 unit. With magnitude. Jeez. Magnitude. Oh my gosh. Are you serious? Magnitude. Let's see if it's gonna. Okay. Of 1 unit. It's like a unit circle, right? Unit circle radius is 1. Unit vector magnitude 1. And usually we denote it as, I'm just gonna leave it alone for now because I don't know what it's trying to do. Oh my gosh. It's trying to insert something. All right. Let me try to figure this out really quickly. What is this? Nope, not what I want. Okay, what are you trying to do here? Undo. Undo? Undo? How do I undo? Okay. I think it's going to pop up again, but we'll deal with it. Theorem. Here we go. For any non-zero vector v, okay? For any non-zero vector v, U denotes unit vector, okay? U denotes unit vector. Unit vector is just simply vector v divided by its magnitude. And it has to have the same direction as your original vector v, okay? Same direction as vector v. As a consequence of this theorem, okay, if U is a unit vector, so if I give you the unit vector and it has the same direction as vector v, then we can find vector v. Then all we do is we multiply. So to find vector v, we would multiply the magnitude of v, okay, to the unit vector. So, and in you're going to find out soon, like, what are the property of multiplication and additions of vectors, okay? 6. Velocity vector represents the speed and direction of an object. Force vector represents the direction and amount of force. Amount of force acting on an object. Okay, so if you don't, if you think of force as like a strength of energy. Okay, so think of force as like strength or energy. Okay. Well, I think I spelled energy so fast that it looks, there's an R right here. Okay. So like later we're gonna find the force to like push the desk around, or find the force if I were to move my file cabinet. So that kind of question. Well, we're gonna find the force of like if you were to, you know, if you're in a wheelchair and then you have to go up the ramp. So those are the sort of the things that we're going to be solving for later, okay? Algebraic vector V. So let's give you the vector notation by hand. Algebraic vector V is, this is going to be like that arrow, okay? In here we have two components, an A component and a B component. I don't know what my computer's doing. It pops up, okay? Where A and B, where A and B are real numbers, okay? Because in the early unit, which is called scalars, okay? So any real number that you see, they're called scalars, okay? Because earlier we also dealt with imaginary, so I want to be very, you know, I want you to understand that in vector we use real numbers here, and these are called components. So the A and B's are called components, okay? Position vector, so let's define that, is where, yes, honey, how can I help you?
Why are you talking?
I'm recording for my students, so we have to be quiet, okay? Position vector is where the initial point is at the origin. Okay, so we draw vectors normally. We draw vectors we're using two dots. One is the beginning, one is the end. So let me just mark in here quickly an X and Y axis. So I'm doing this all without a ruler, so it might not be as straight. So the position vector is, instead of starting here and ends here, so this is dot 1, dot 2, we are going to, let's call that V, okay? So position vector is, I'm going to move it just down to the origin. The reason I move it to the origin because it's easier to add and subtract and so on and so on. So it looks like, let's see, my dots are, I went up 3 and went over 2, 4, 6. So we're going to go up 3, 2, 4, 6. So this is the same vector, okay? Same vector. In drawing out vector, you can draw it anywhere. But to put it at the position, it's just easier, okay? So this position vector, it's starting at the origin, so that's why it's called position vector. But in terms of the size and direction, they're exactly the same. All right, resultant vector. Because later we will be solving applications and it's going to ask for resultant vector. So the resulting vector is the combination of two or more vectors. Good morning, honey. You okay? One of my daughters.
Sometimes I do that on purpose because they have a little bit of mucus and like that.
Oh.
So sometimes I do it on purpose to get it out.
Suppose that V is a vector with initial point P. Let's call it P1 because we're gonna have 2 points here. So P1 it's some x1 comma y1. Not necessarily at the origin, and the terminal point is called P2. It's called x2 comma y2. If vector V, okay, it's from P1 to P2, then V is equal to position vector. Call it position vector. Let's denote it with the vector symbol equal to. So this is how we find your V. We're going to subtract the two x components, okay? And we will subtract the two y components, okay? So what do I mean by that? Let me give you just quickly. So let's give you point 1. In the definition, they use x1 and y1. I will give you extra points, okay? Let's call it 8 and 4. Okay, that's your point 1. Then let's give you point 2. In our definition above, they give you x2, y2 are the two components. I will give you 14 and 7. Okay, so those are the 2 points here. So we are going to plot. So we're going to assume that this is always in quad 1. Okay, so this is the origin. Oh gosh, this is the origin. Okay, so I'm going to plot 8, 4. Okay, so but we're going to move it down to the origin later. So that's where our position vector is going to be. But where on earth is 8.4? So let me plot 2 points. 2, 4, 6, 8. Go up 4. 2, 4. So that's 8, 4. That's point 1. Okay, and then 14. That's 8, 10, 12, 14. Up 7. 2, 4, 6, 7. So this is point 2. We will make an arrow to denote that this is a vector. So let's bring this vector to the origin to call it position vector. Again, we went up 2. Okay, so look at this. How do I get from one to the next? Think about slope. Okay, rise over run. So let's count 3. 1, 2, 3, because that's the run, and over 2, 4, 6. So 2, 4, 6. We can just totally count. We can just count. Okay, so this is called vector V, or we can do basic math. So I said, hey, to get position vector, you subtract the two x's. Okay, so x2 minus x1, which is 14 minus 8, comma 7 minus 4. Okay, so V equals 14 minus 8 is going to be 6. Okay, 7 minus 4 is going to be 3. So what's happening? Because I only keep in mind that we don't need you know, a lot, because it's already starting at 0, 0. So what it's telling us is that x direction is 6 and y direction is 3. Okay, so this is vector v is components of a comma b, or oftentimes it's going to be x comma y components. Okay, all right, here we go. That's how we find position vector. 12. Theorem of equality of vectors. Two vectors, let's call it v and w, are equal if and only if their corresponding components are equal. That is, if vector v equals a comma b and vector w equals a, let's call it a2 now, comma b2, because we have two a's and b's. So let's insert in vector v a1 and b1, okay? So vector w a2 b2, then vector v is equal to vector w if and only if a1 is exactly the same as a2 and b1 is exactly the same as b2. So what do I mean by this? So let me give you some vectors. Okay, I'm gonna put some points on here. So let's do point 1 is going to be point 1. Let's put it -6 comma -6. Okay, point 2. Let's do -1 comma -3, and let's make the x-axis now right in the middle and the y-axis right in the middle. And plot those. Okay, so here we go. -6, 2, 4, 6, and down 6, 2, 4, 6. There's your first point. -1 comma -3. I'm just trying to make a vector here. Okay, so that is going to give me one vector. Let's call this vector what? W or v? V first. Okay, let's do another vector. Point 3. Okay, 1 comma 3, and point 4. Let's do 6 comma 6. So 1 and up 3 and 6, 2, 4, 6, 2, 4, 6. I'm just plotting points, no worries. Okay, let's call this vector W. Now, these two are totally in different location. Okay, two different locations. How do I know that they are the same or equal vectors? In this case, it's called. Well, vector V. Oh, let me use the same color as the vector V. Vector V, how do we find vector V? We have to take the components and subtract, right? So we can use x2 minus x1 comma y2 minus y1. So that will give me x2 is going to be -1 minus a -6 comma -3 minus a -6. Two negatives and make it a positive. So that's really now -1 plus 6. So that's going to be 5. -3 plus 6, that's going to be +3. So those are, excuse me, that's a component of vector V. Now vector W, we are going to use the same formula, okay, and we're going to use the point. So x2 for W vector is 6 minus 1, and then 6 minus 3, those are the y's. 6 minus 1 is 5, 6 minus 3 is 3. So check it out, the components are exactly the same, even if they are in different location. So these two are now equal vectors. Adding vector geometrically, okay, geometrically. So yes, you can totally add vectors. Can you believe that? Okay, so we are going to do vector W plus vector V, and in adding vector, it is commutative, so it's the same thing as vector W plus vector V. Okay, so V plus W is the same as W plus V. And again, we're going to assume that this is just quadrant 1, so I don't have to draw out the x-axis and y-axis. Okay, so I'm just going to randomly draw, let's do the vector W first. Let's start at somewhere that's not at the origin. So how about here? Oh my gosh, okay. How about that? That is up 3, right 2. Okay, up 3, right 2. So that's, I'm just trying to create a vector. and then let's count together. 2, 3. So go 3 and then maybe 4. Go 3 and 4 to the right. So let's call this vector W, something I made up. That keeps popping up and it's quite annoying, but I'm just going to ignore it. Then I'm going to get another vector. Okay, let's count 2, 4, 6, 7, and then go down all the way here. Okay, so right 7 and down 2, 4, 6. And connect these two dots. This is called vector V. Adding vector. So this is the part that's really, some students get it wrong because of this. This is our starting location. Okay, starting location, starting point. So starting point is there. So when you add vector, okay, so you continue to draw them. Okay, you are continuously drawing them. So wherever W ends, you continue with V. But when you find the summation of the two vectors, then you start here and you end here. So this red vector is where vector W plus vector V, which is the same thing as vector V plus vector W. Okay, so this vector W is the final answer, if I can highlight that, of the two adding together. Next, we also have adding 3 vectors together. Okay. One of my daughters has a question. Yes, Stevie.
How long will this take? This is all boring.
Well, this is really difficult for our students. Okay, vector
I don't know it.
Vector U, okay, plus quantity of vector V plus vector W is exactly the same as vector U plus vector V plus vector W. Okay. All right, my daughter thinks this is boring. I'm pretty sure you guys think the same, but it's so important, so we have to get through it, okay? And again, we're going to assume that this is going to be in quadrant 1, so I'm just going to randomly draw a vector, 3 different vectors here, so bear with me, okay? So let's draw some short vector U, because I don't know how much space I have. So go up 3, right 2. So let's call this vector U. Okay, I'm going to add vector V. So now I'm gonna go down. Okay, so just to make it unique. So 2, 4, 5. Let's do right 5 and down 4. How about that? Now, again, when you're adding vector, you continue where you left off. So let's call this vector V. Okay. Then I'm going to draw vector W. Let's make vector W all the way up. Okay. So let's see. 2, 4, 6, 6, and then 2, 4, 6, 8, 10. How about that? So this is how we add them. Okay. So we continue where we left off the other one. Now, but when we find the answer, keep in mind the starting location. The starting location is right here. Starting point, right there. We have to use that starting point and we go all the way to the end. So this red vector is where U plus V plus W. Okay. Now we get a different color pen and then sort of go over where this right here, this green one is where U plus V is. Okay. Now I'm going to use another color here to kind of demonstrate where this one. Okay, let's use this color. I'm going to demonstrate where V plus W is. Okay, so V was here, okay, and W ended right here. So this right here, in that color, okay, is where V plus W is. Okay, so but to have U plus V plus W is the red one. Okay, wherever the starting point is, where the end one is. We just have, let's see, we'll stop at over here, these last two. Next one, we have, what if you add 0, okay? Remember, 0 vector doesn't have anything. So V plus 0 vector is the same as 0 vector plus V, because it's commutative, which is the same thing as magnitude V. So let's make up magnitude V right here. And I don't know how many points is that. Go up 1, 2, 3, 4. 2, 4, 5. Go up 4, right 5. what does it really mean to add vector v? Vector v doesn't have any size, right? So adding vector v is, it's sort of just a dot. So if you add vector v is this length, vector 0 is a dot, okay? It doesn't have any directions, it doesn't have a size, so it's just a dot. Well, if you're adding nothing to vector v, then you just have vector v, okay? Last one, here we go. What if you add vector v to its negative vector? Then you get vector 0. Negative vector is the opposite direction. Oh, how annoying is this? 2, 4. Oh my gosh. 2, 4. Let's go 4 and then go over to the right 2. Are you serious? Okay. There you go. 2. Let's call it vector v. What does negative vector looks like? Negative vector is starting at the same location, but you go opposite direction. So technically, I can put this negative vector anywhere. Remember that, right? Position where it is located is not important. It's just really the size and the direction. So because I went up 2 and right 4, technically, class, I can start here, go down 2, 4, and right 2, okay, and draw the arrow the other way. This is a negative vector v. So when you have a positive vector v and adding its negative, you go back to where you started. So because where you started, then you cancel out the size, then what you have left is just a dot. Because what you have left is the dot, then it's just a vector 0. We have just, I think, 2 more, maybe 3, 4 more definitions here. So let's continue with multiplying vectors by numbers geometrically. So again, I'm going to use quadrant number 1. I'm going to make up a vector v here. Let's start here. We are going to go up 2 and let's see, 5. Okay, so go up 2 and then 5, 2, 4, 5 to make vector v for me. So go ahead and draw a vector v. All right, so there's a given vector v. It says in the box, if alpha is a scalar and v is a vector, the scalar multiple alpha times v is defined as, number 1, if alpha is bigger than 0. I mean, if alpha is positive, then alpha times v is the vector whose magnitude is just as many times, okay, just as alpha times the magnitude of vector v, and whose direction is the same as vector v. So, i.e., if I want to go and do 2 is your scalar, 2 times v. So what that means is, according to number 1, is that, okay, well, now it's just twice as long as v. Well, v was up 2, right 5, so now I'm going to go up 4, 2, 4, and then right 10, 2, 4, 6, 8, and 10. And it said in the direction is that it still goes the same exact direction as the regular v, the original v. Now, if alpha is negative, alpha times v is the vector whose magnitude is still the same number of distance, okay? But because you can't have a negative length, so now it's just an absolute value, alpha times the magnitude of vector v, and whose direction is the opposite as v. So, i.e., if we have negative 2 times vector v, instead of going the same to the right, we will go to the left. So I'm going to put a dot here. We knew earlier we were going up 2 and right 5, so now we're going to go down 2, okay, and then left 2, 4, 6. I'm sorry, 2, 4, 5, and then do it again, down 2, 2, 4, 5. So what I'm doing is I went down 2, left 5, down 2, left 5, or you can do down 10 and then left. Down 4 and left 10. So now this is really a negative 2 vector v. This is really 2 positive v. If alpha is 0, or if either vector v is 0, then alpha times v equals 0. Okay. So here are some properties. We got 0 times vector v is going to be 0 vector or just 0. 1 times vector v is going to be vector v. -1 times vector v equals, sorry, I'm missing a -1. So -1 times vector v is just a negative vector v. If we have two scalars, alpha and beta, and we're going to multiply vector v, it can be used a distributive property, just like that. Then what if we have alpha times vector v plus vector w? Then we can go and distribute that again. So it can be alpha times vector v plus alpha times vector w. Now what if we have alpha times vector v, but vector v was already multiplied to vector beta? It's okay. We can go and move and get alpha times beta first, though two scalars multiply each other first, and then we can multiply by vector v. Add and subtract vectors algebraically. So let vector v be a sub 1 times I, remember I is in the left or right direction, plus b sub 1 times j, j is up and down. So we can just write it as a1, b1. And vector w is a2i plus b2i. We can rewrite it as a2 plus bi without the direction. Our two vectors, and let alpha be a scalar. Then one of the properties says if we're adding vector v to vector w, so now if we're adding this algebraically, we can go and take a1 plus a2, and then if you want direction, then we put vector I on it. Then we can go, you know what, let's get rid of this right there, there you go. Then we can go b1 plus b2, and for the j direction, so the j is up and down, which if we just want to know the length without direction, then this is where we put a1 plus a2 comma b1 plus b2. So when you see it written like this, the end right here, that means without direction. Okay, let's do v minus w, very similar. We can get a1 minus a2 in the I direction plus b1 minus b2 in the j direction. Now if we do not care for direction, we can go a1 minus a2 and then b1 minus b2, just like that. How about alpha times vector v? Well, we kind of saw this earlier in the previous definition. We can go alpha times a1 in the I direction, then we can go alpha times b1 in the j direction. Now we can say, okay, well, alpha is, let's just say 2, then it's just 2 times a1. If alpha's, that's twice the length of a, then if, again, alpha is 2, then it's 2 times b1, twice the length of b. Now we have this definition here. This is an absolute value, and in your book they use a double bar. So an absolute value of v means the magnitude of v, which is a squared plus b squared all under the square root. Remember, this is also the same definition as the radius, okay? Find a vector from its direction and magnitude. So if we have a vector v, and if we want to find a vector from its direction and magnitude, then here's the formula. Vector v equals the magnitude of vector v times cosine of theta in the I direction plus sine of theta in the j direction, where theta is the direction angle between vector v and I. And remember, vector u equals vector v divided by the magnitude of v, which if we were to multiply and then solve for vector v, we get vector v equals vector u times the magnitude of v. Okay, let's try to understand this from a unit circle. So we will try it up. Here we go. Here's a unit circle. We're going to invade the other side. Actually, let's make it this side and then because we're going to have to use that in a little bit. So I'm going to use, okay, so let's say that we have a unit circle. I mean, the radius of this whole circle is 1. And let's say that this is a unit vector because it's on the unit circle. We don't know this theta. We don't know that angle. Let's call it theta. Theta could be 30, okay, it could be 60, whatever angle that we want to use. So this dot right here, class, is cosine of theta times sine of theta. So that's pretty much x comma y. There's a dot. So we have a unit vector, we have an unknown angle. Now we also have our I direction, right, which is on the x-axis, so I vector, and we have the j direction, which is on the y-axis. Would you agree with that? So since it's a unit circle, I'm going to make the I just within the unit circle. What this is saying is that, okay, well, what if I want to find what vector v is? Well, vector v currently it's unknown. So what if we said, what is this unit vector? This unit vector can be written as cosine of unknown, because that's how long the x-axis is, times I vector, because that's horizontal, plus sine of theta in the j direction. That would give us cosine of theta I, meaning that I'm going this way, and then I'm going to add this way to give me my vector u, which is the unit circle. Well, then it said, okay, then that's this piece. Okay, so that's that green piece. That's the cosine of theta I direction, sine of theta in the j direction. It's giving you your unit circle, which is this guy right there. Well, what if, then how do I know where vector v is? Well, it says, okay, then take unit vector and times the magnitude of v. V, let's say, what if I want v to be all the way like that? Okay, this whole thing is v. How long is the magnitude? Magnitude is the radius, right? Magnitude is the distance from the center. So if I know the length by finding it algebraically, which is the square root of a squared plus b squared, then I would know the entire vector v. Okay, so this right here, guys, this piece right here is just a unit circle, okay, in polar. All right, let's go to our last definition here. It says direction angle, and we kind of use that above in the upper definition right here, direction angle. So direction angle is restricted only in between 0 radians and 360 degrees, or you can use you can use radians between 0 degrees and 360 degrees, inclusive of 0. You can use also radians. Okay, now to find the unknown angle, we are going to resort back to tangent inverse of y divided by x, and don't forget to check for the correct quadrant. Okay, check for the correct quadrant. Make sure you add a pi or 180 degrees if it's not already in quad 1 or quad 4. Okay, if it's in quad 2 and quad 3, make sure you guys check for the correct angle. And that's the end of the vocab.